Hello everyone, hope all is well today. My name is Jelamat. Today we'll go through a discussion concerning the t-test for unpaired data, and that is to compare means from independent populations. Okay, I'm going to assume that you have two numerical variables, one called x1, the other one called x2. These are your samples from your two populations, and I'm going to use the t-test function to compare the means. It's quite easy. It's called t.test. We put in the as arguments x1 and x2, and this will be testing the null hypothesis that the means are equal against a two-sided alternative that the means are not equal. To use a right-sided alternative, we can add the argument alternative equal to greater. For a left-sided alternative, we can add the alternative equal to less. And by default, we'll assume that the population variances are not equal using the Welsh approximation for the t-test. If it's reasonable to assume that the populations are equal, population variances are equal, we will add the argument var.equal equal to true. Okay, so let's go through an example. This is a simple example where I'm going to use the C function to assign values to the variables called x1 and x2. In a part 2 of a video for independent populations, I'll show you how to do this when importing data from a file. Okay, and so I'm going to use the C function to assign my data to x1 and x2. Now I have x1, x2. I'm going to, first of all, before using the t-test function, I'm going to produce side-by-side box plots and overlay normal probability plots for my two numerical variables. Okay, and so I will need two functions, one called ppnorm, the other one called boxplot, inside of a file called plots.r. And these are functions that I defined for you to be able to produce these plots. And so we're going to source the file. So it's source, and then I'll do file.choose. This is going to force R to ask me where is this file that you want sourced. And I put it in my documents. The name of the file is plots.r. Okay, one function is called ppnorm. The other one is called boxplot, capital B, capital P. And then if you properly sourced the file, you should see the following output when you enter ppnorm and boxplot, capital B, capital P, and at the prompt. Okay, and so now I'm going to create a graphics window which has one row, two columns. So I use the function, the command called par. It's mfrow equal to C. I have 1, 2, so one row, two columns. So this creates a graphics window with one row, two columns. And then now I'll use boxplot, capital B, capital P, of x1 and x2. And then ppnorm of x1 and x2. And then when I go to my graphics window, I see I have two plots. I have one row, two columns. I have the side-by-side box plots and the overlay normal probability plots. Linear tendencies in the plot, so it's reasonable to assume equality variance, even though there's slight deviations in the tails, but that's fine. And then if we compare the boxes in the box plot, we see they're very different. And also the slopes in the normal probability plots are very different. And so we have very strong evidence against the equality of the population variances. So it's not reasonable to assume that my populations have equal variance. And so we'll use the Welsh approximation for the t-test. And so to do the t-test, we'll do t.test of x1, x2. By default, it's going to be the Welsh approximation. I have the observed value of the t-test statistic, degrees of freedom according to the Welsh approximation, corresponding p-value to test an alternative that the true difference in mean is not equal to 0. So this is a two-sided alternative. We also get a 95% confidence interval for mu1 minus mu2. If I only want to display the confidence interval, I can add to the command $conf.int, and this gives the 95% confidence interval. I can also change the level of confidence by adding another argument called conf.level equal to, and then I put in the level I want. Let's say I want 98%. And so here I have a confidence interval for the difference between the means, so for mu1 minus mu2, at a level of confidence of 98%. Okay. Now, let's assume that we did not want to test a two-sided alternative, but rather our research hypothesis was that mu1 is going to be larger than mu2. And so I'm going to add in an alternative equal to greater, and then I'll have the corresponding p-value for an alternative that is the true difference in means is greater than 0. If my research hypothesis was that mu1 should be less or smaller than mu2, so then I would use an alternative equal to less. Okay. Now notice that in both cases where I use an alternative equal to less or alternative equal to greater, the confidence interval that is given is actually not a confidence interval. It's actually given us a bound. And so here I'm 95% confident. So in the case where the right-sided alternative, I'm 95% confident that the mu1 minus mu2 is larger than 13. So we're highly confident that the difference in means is actually greater than 0. Okay. In the case of a left-sided alternative, we're given, again, a bound. So here we're 95% confident that the mu1 minus mu2 is less than 68. But this means that we're not confident that the difference between the means is negative. Okay. Anyway, we can just use the p-value to interpret or to test our hypotheses. So this is an example where I use the Welsh approximation. And let's now go to our example 2. Again, I'm going to just redefine or submit the data using the C function. And I'm going to define a graphics window, par mfro, which is going to be of size 1 by 2. And then I put in my box plot, capital B, capital T, P, sorry, x1, x2, and then pp norm of x1 and x2. And then if we go to the graphics window, here we see that, again, linear tendencies and the normal probability plot, so it's reasonable to assume equal normal populations. And then when we look at the box plots, the widths of our boxes are similar. They don't have to be equal, but they should be similar if we weren't to assume equality of variance. And then we have our lines, which are not parallel, but they're approximately parallel. Okay, so the slopes are not very different. And so it's reasonable to assume that the population variances are equal. And so I'm going to use students t.test now to compare the means. And so I'm going to use the t.test of x1 and x2. I use the argument var equal to true. And this will give us a two-sided alternative. P-value here is just a bit more than 4%. It's a two-sample t-test. It's not Walsh approximation. And if I wanted to get a confidence interval, I just, again, like before, add $ with conf.int to my command, and I get the 95% confidence interval. All right. So this is how you do the t-test, or use the t-test function with R for testing the equality of means from independent